Okay, well, welcome everybody. Pleased to have you for our second or third seminar of the semester. Very pleased to welcome Professor Yunan Yang from Cornell University. Yunan obtained her PhD in mathematics in UT-Austin in 2018, working with Goenka. And then she was a Quran instructor at Quran in New York, and a fellow at an advanced fellow at ETH, at Institute for Theoretical Studies there, and has won a whole range of interesting prizes along the way in her career, including the IMA Leslie Fox Prize in Numerical Analysis in 2019, the first prize. And her interests are broadly in computational mathematics, in inverse problems, numerical analysis, optimal transportation that we'll hear about today, and the intersections with machine learning as well. So I'm really pleased to have Yunan giving talk today, and please take it away.
Yes, thank you very much for the organizers and having this opportunity to stand here to present one of my two of my favorite topics. One is optimal transportation, and another is the inverse problem. So just from the starting point of my PhD and today is exactly a decade, and I'm very excited to share how much I have learned and also my insights on how to combine these two together. So I would like to begin with inverse problem. Inverse problem, if this is the first time you have heard about it, I always want to put it side by side with what we call forward problem. So forward and inverse, not only English-wise, they are counterpart of each other, but also in the mathematical side, they are counterpart of each other. So when we talk about forward problem, you can think about that you know the model, you are given, let's say, a partial differential equation or reliable graph model or neural network model. You are also given other things like initial condition, boundary condition, source term, domain, boundary, and also the variable coefficients. In engineering, you probably deal with a lot of more complicated PDEs. So you are given everything, then the goal is to simulate the physical coefficient or physical variable as accurate as possible, so that what your simulation can produce will match the real measurement, real data. So this is what I consider as a forward problem, because you try to make sure the computer simulation is really realistic. And in this process, you have everything. All the physical parameters are given. While inverse problem is the opposite. So you are given instead some real data reference or functions of those solutions of the PDE. And the goal is that, can I infer what is the initial condition, or what is the boundary condition, what is the variable coefficient, and what is the best way to find them? So that's the study of the inverse problem. So we go from the data towards the data with the model, and then go into the parameter. Some of the very notable inverse problems, for example, in what I have been working on is about seismology. So let's say an earthquake happened, and we observe data as the tremors that on the surface, and the goal of geophysicists is to detect where is the earthquake source, how deep it is, and can I find out the impact of it in the next few hours. So that's one inverse problem. And a few years ago, we also have another new inverse problem that can be practically done, which is image the black hole. So we receive photons on part of the Earth, and can we utilize those photons effectively such that we can image the black hole? So that is the inverse problem. And more commonly in the hospital nowadays, we can run into day-to-day basis is to do X-ray, CT, and ultrasound. And they are inverse problem in the sense that signal goes through our body tissue, and the devices receive it one way or another, and the software will process those signals to reconstruct our body tissue. So that's inverse problem. And the inverse problem can be purely imaging without PDE, or can be with earthquake source type of problem that has a PDE. So most of the time, I work with inverse problem that has a PDE model. And in the following, I'm going to generalize a little bit. So inverse problem, in my view, has two most important components. First of all, I have to have data. Without data, I cannot say anything about the parameters. So the data usually come in pairs, like X can be the probe into a model, a system. So for example, that can be the earthquake source. So source is the reason that we receive displacement on the surface. And so that's the data. And then we receive the result of it, and that will be what the seismic station can record all those wiggles and the waves. And so data is one component. And another component is what's the model. So when I deal with waves, I need to identify which is the model that I want to use to model waves. So for example, I can turn to acoustic wave equation if I'm dealing with ocean-based waves, or I can go to very more complicated elastic wave equation if I'm on the land, where I adding more and more components to incorporate damping and viscoelastic. So we can go more and more complete in that direction. So with these two components available to me, data and the model. How to infer the coefficient in the model is what the study of inverse problem is concerned about. And this model can be PDE, or can be graphs, or can be your neural networks. So that's my view of more generalized inverse problem. And when it's formulating like practical inversion, most of them you find shadows or closeness with supervised machine learning. Yeah. So in the following, I'm going to give you a few inverse problems that I work on a lot. So first of all is the waveform inversion, or sometimes called full waveform inversion, FWI. So in full waveform inversion, the example can be an earthquake happen, and then that could be the source like in between two slabs, and that give me a fault, and there's a displacement. And this displacement between these two slabs is going to generate a source, and the source propagate along all the materials. And when it comes to our surface, we kind of discover the displacement. And the data we receive are those wiggles. So the black means negative, white means positive. So they are like sine and cosine, or complicated superposition between sine and cosine. The goal is using those data, which we regard as the PDE solution at z equal to 0. So z equal to 0 means I'm at the, really the surface of the half plane. Using those data, can I find the variable coefficient 1 over c squared? So this is the wave equation. Usually when we learn it in PDE course with Evan's book, the m of x is typically regarded as 1. But in real situation, we always deal with variable coefficient wave, or because the material in many, let's say Earth, or even our medical imaging in our human tissue, they are variables. And it's exactly those variations that tells us the structure, and it tells us the difference between muscle and the bone, between water and the rock. And the difficulty of such inverse problem is, although this is a standard second order hyperbolic equation, is linear, but the relationship between m and u is highly nonlinear. So in PDE class, we learned the linearity from s to u, but what we are interested in here is really using u to find m, and that relation is nonlinear, and that's the whole difficulty of getting m out of it. So that's a time-dependent wave equation. And also when we deal with it practically, that will involve solving the wave equation again and again in an optimization framework. And this wave equation, as you can see, has time domain dependence. So that means when I simulate it, I probably need to do time marching. Although we can do time parallelization when solving the wave equation, still there are instability issues. So 90% of the time, we will actually have to do forward time marching, which means you have to suffer from CFL condition. So that makes the wave simulation very expensive. And in practice, one realistic Earth-related wave simulation can take half an hour per solve. So based on this difficulty, people also consider the corresponding Helmholtz equation. To translate from the wave equation to the Helmholtz equation, we assume the solution is time harmonic. That means I can take a Fourier transform. So once I take a Fourier transform with respect to the time domain, time diminished, and instead I have frequencies. So now we have the frequency omega squared. But what's nice between these two models is the m in my previous wave equation also become the m in my Helmholtz equation. But the beauty of solving Helmholtz equation is that I can solve it in parallel in frequencies. So that can boost a lot of the computation efficiency, and people also solving exactly the same inverse problem would use Helmholtz equation as alternative modeling, just because we can gain a lot more efficiency in the forward simulation. Let me see. Okay. So if we don't think about from a wave inversion perspective, Helmholtz equation with variable coefficient to be detected is also related to a very large domain of inverse problem called the inverse scattering. And that has applications in radar and in optics. So that standalone is also very important. So that is wave and Helmholtz. The next example I want to give you is a kinetic equation. So on the right-hand side, I wrote down the Boltzmann equation. So Boltzmann equation is a model if you want to study the behavior of rarefied gas. So the left-hand side of the Boltzmann equation, if you forget the complicated right-hand side term, the left-hand side term alone is purely a transport operator. You will see very often, or in any course that about fluid dynamics, it's just a transport operator. But the right-hand side is where we can model the rarefied gas. So the F1 term means the moment I have a collision, two particles they collide, the velocity the two particles they have before will diminish. So that's why we have a loss term. But because the moment they collide, all the velocity is gone, new velocity are created, and that's why we have a gain term. So using this way, you can relate when we play pool, right? We hit one ball with another, so the moment these two balls collide, their original velocity change, so they are gone, and the new velocity will make them move. So really the right-hand side is characterizing this loss and gain process at a certain rate. So Q is characterizing how often and in which capacity this colliding is happening. So that's the Boltzmann equation. And they play a very important role in gas modeling and also nowadays towards fusion plasma. And then an interesting inverse problem will be, okay, I'm going to design a channel such as a gas will flow inside the channel. But when I do the design of the channel, I have a design principle. I want to make sure the temperature, for example, of the gas is going to be not so high. Because when the temperature of the gas is too high, I can burn my material. So one possible design principle is to say at a certain domain of this subset of the domain, I want some microscopic quantity, such as the temperature, to be low. And in this particular design problem, which also you can think about as an inverse problem, we will need to deal with a lot of like optimization and also difficulties of working with such a very complicated integral differential equation of 12 dimensions. Okay. So another problem is dynamical system that I start to get into in the latest 5 years. So dynamical system come from all kinds of backgrounds, such as aerodynamics and biology or social science. So the setup is the following. Let's say we can observe the birds flocking, and we have a tracker on the bird. So after a certain period of time, we observe the location or position of the birds at discrete measurements. So that means we may have such a trajectory. And we observe such a trajectory in space, and maybe we also assume that the underlying model is this ODE, and I want to use those trajectories to be able to model what is right-hand side dynamics, which is the flow velocity V. And the V can be parameterized by my favorite way of doing that. Alternatively, if you assume the underlying dynamics you observe is noisy, and where is noisy intrinsically, then you can go also one step away from the deterministic ODE to the stochastic differential equation, and that's a new model. And based on these two models, you can there's actually a whole community of works about how to use trajectory data to find such V in either SDE or ODE. One of the very notable methods is SINDI, where the velocity is parameterized by a linear combination of polynomials, and or neural network based, and that is a method called neural ODE in 2018 that also very impactful. And other parameterizations also exist. So in this work by Lu Fei, Mauro Maggioni, and Sui Tang, they were using other piecewise polynomials. Okay, so that if I want to solve the problem on the Lagrangian level, which means I'm tracing the particles. Alternatively, we can actually turn those ODE model into a Lorentz framework, and that will give you either continuity equation or the Fokker-Pond equation. So this model, if I use it, then I will actually deal with a PDE-constrained optimization. So this is what I have been focusing on, and where optimal transport can play a role when you switch from Lagrangian description to a Lorentz description of the same flow field. You can use major theoretical methods to gain a lot of more stability. Okay, so I give you a sequence of PDE or ODE or SDE-based inverse problems. They are, what they share in nature is they are all nonlinear. The nonlinearity come from not the PDE or ODE by themselves. Those are all linear problems, but they really come from the relationship between the V, for example, which we want to find out, versus the data that we can find out. So that is really the intrinsic difficulty of solving such inverse problem. And the more nonlinear the relationship from X to V or to theta, the more difficult it is. And on practical perspective, I cannot easily solve the inverse problem just based on like a basket of data and two PDEs. I need to find a practical way of doing that. And that practical way in inverse problems is always the inverse data matching problem. So rather than saying I have this forward model F, and I have the data little f, rather than saying I'm working with the equation, try to use the data to find an M, we use an alternative framework by finding what is the best M that can minimize the difference between what I've observed, G, versus what I can simulate. So this is similar to when we deal with linear algebra. If you have an overdetermined system, you know the solution does not exist or it's not very easy to find. So what we do is we formulate it as a least square minimization problem. So here the transition is very similar. You have a very nonlinear equation to solve. And sometimes in PDE or ODE, this F, you cannot even write it out. You can only simulate it, but you cannot write it out because the solution is not analytic. So in that framework, a workable way of solving the inverse problem is really translate a root finding type of thing to an optimization framework. And then that gives us at least optimization problem that I can throw in mature optimization techniques, such as gradient descent or BFGS. So that is a transition. So what I present here is a deterministic path to attack some of those inverse problems, but what Yusuf and many others here, you work on the Bayesian side, which is also a very nice way of dealing with them. And in this talk, I focus on the deterministic side of inverse problem. So once we formulate from an inverse problem to an optimization problem, there are two things we need to be careful. Usually we were not, at least I wasn't at the very beginning of my career. And now I want to be more careful about it. One thing that you need to be careful is which metric or divergence or discrepancy I want to use to quantify the difference between F and G. So G is the reference data, F is what you can simulate. You want to match them as closely as possible so that you can find the best M. So whenever you choose this DG, D sub G, which is the discrepancy, you already assume in which space, in which like a box you are trying to find the problem. For example, if you use least square method or L2 norm, that means you intrinsically believe your data should belong to L2. So that means certain regularity in it. But if you use, let's say, H1 norm, which is a higher order Sobolev norm, that means you underlyingly, like intrinsically believe your data is smooth, have at least a first order generalized derivative. And if I'm using Wasserstein metric to quantify the difference or KL divergence, that means I'm assuming they are probably distributions. While using KL divergence means you're assuming the distribution are absolute continuous with respect to the underlying, like a baseline, let's say the big measure. By using Wasserstein, that means you also get that off because Wasserstein is capable of measuring the difference between direct delta and empirical distributions. So each time you put something here, you already insert some assumption about which space you are trying to find the inverse problem. Okay, the second place that we need to be careful is the argument side, like in which space I'm trying to find the best parameter M. And so let's say I try to find the solutions that is in L2, that means you just want the solution to be square integrable. But if I'm trying to find the solution in a polynomial basis, that means I want everything to be C infinity. So the smoothness is also kind of enforced in the way that where you are going to find the M. Okay, so what I want to emphasize is without really changing your model, and also without changing your data, just because you choose these two metric spaces differently, you can significantly impact the result of your inversion, and consequently both the speed and the quality. And that is what I want to convey. And in my research, I heavily use optimal transport and the Wasserstein metric in either of the two places. And I want to show why in those scenarios, using optimal transport will be better and also help you to go beyond what the classical method cannot tackle. Okay, so now that we come to optimal transport. So optimal transport is a very, not very new subject. It was proposed by Gabriel Monge in 1781, I think right after the French Revolution. And Monge, as an engineer at that time, has this very practical problem. He has a pile of sand. They are doing a lot of constructions after the revolution. So he wants to put this pile of sand, move to another place that has equal total mass. And now, because it's not a single atom that we can consider, it's really a big volume of stuff. So you have multiple choices. You can do left to left, middle to middle, right to right. So you can do a monotone in that way, and that's one plan, or that's one map. Another map is to say middle to left, right to middle, or left to right. So that's another one. There's infinitely many ways, and the question is which one is the most efficient? So that's the question Monge asked. The question is very easy to formulate and explain, but it's extremely to solve for two reasons. First of all, Monge is searching for a map, which is a function that maps from one domain X to another. And that is an infinite dimensional problem without any restrictions. And at that time, before calculus even getting very mature, solving an infinite dimensional problem is not something can be done very nicely. And the second reason is once we write it down, what is a minimization objective function, then you can see it is also nonlinear with respect to the map. Not only you are searching in an infinite dimensional space, but the problem is also nonlinear. So that's why there's nothing going on for almost 200 years until Kantorovich, who relaxed the problem a little bit. Kantorovich come into the image saying, oh, you are searching for a map. How about I relax in the sense that I allow mass from a location X to be split, to go to both Y1 and Y2 and potentially Y3. So the moment that you map X to 3 or 2 different places, this is no longer a function. It disobeys the fundamental definition of function. And that's why you have a plan. The moment you have a plan, you relax the problem by a lot, and Kantorovich was able to rewrite it as a linear problem. Still infinite dimensional, but now at least it's a linear minimization problem. And at the moment, due to the computer science boost, so people can solve it practically by linear programming. And this also was used a lot in resource allocation. And that eventually got Kantorovich Nobel Prize in economics in 1975. And the late 20th century, there's so many really good mathematicians working towards it, and the list is by no way near complete. So they contribute to all aspects of the theory and make it a really complete and self-contained, beautiful mathematical theory that in optimal transport. And starting with that, all the solid foundation in analysis, we see very nice boosting applications in various fronts of applied math, including data assimilation, hyperbolic model reduction. Yeah, model reduction has been studied for 2 decades, and most of the difficulty is can we reduce hyperbolic PDEs, because the kernel growth NVIS is very bad. But many people have tried, how about I do model reduction not in anisotropic spaces, which are linear. How about I do it in Wasserstein space, which automatically has transport nature. So there has been some success and continuing workings. And the image processing, it can trace as early as what Tony Chan did in early 2000, right after the Barnum-Brunier formulation. And there's also many more later on. Inverse problems, machine learning, and sampling and more. There's a lot of actually MIT faculty that have learned about this application along the way. And again, this list is nowhere near complete. And I have a perfect excuse for that. So this is something I learned by reading a paper by Diane Spletchev back in 2016. Oh my God, it's almost like 8 years ago. So in that paper, as a graduate student, I feel so motivated because on the very first page of his paper, he has this trend from very early on, like say late 20th century towards to late first half of 2016. And I saw this boost and I felt like I'm in the right field to study it. And today, after 8 years, I was able to complete a bit more. So just in last year alone, there was 8,000 papers, more than 8,000 papers that contain keywords such as optimal transport, Wasserstein, Monge, Kantorovich, or Earth mover distance, which is one that computer scientists use. So this increasing boost of research activities is one excuse that I can never make the list complete, but also shows you that in all different kind of applications in beyond pure analysis, that we find usefulness of optimal transport. Okay. So another 2 things that whenever I explain this to my colleagues in the math department is that optimal transport is not just a field, a subfield in analysis. It really branches out to other areas of mathematics. One is the seminal work by Yunan in 1991. So Yunan have this very good result saying, if I have this quadratic cost, when I measure how expensive to go from X to Y, if it's quadratic, like squared Euclidean distance, then I have a more characterization of the map. And the map has to be a gradient of a convex function. So now you are not only searching for infinite dimensional function space, you also search for gradient of something. Okay, together with conservation of mass constraint, you would easily derive this Monge-Ampere equation. And the Monge-Ampere equation is exciting not because it just showed up in 1991. It actually can be studied in another field of mathematical differential geometry since late 19th century. So this connection really incorporate optimal transfer to be in the geometric measure theory study. And another very nice branching out connection is this famous Jacob O paper with O standing for Felix Otto. So in this work in 1998, the observation is for those PDEs, like heat equation, linear Fokker-Planck, porous media, and McKean-Vlasov equation, important equation in kinetic theory, again, studied more than half a century. Suddenly, I can rederive all those equations as a gradient flow. But the gradient flow is not like gradient flow in L2 gradient. It's not even gradient flow in H1 or H-1 gradient. But it's going to be the gradient of the Wasserstein metric. Because Wasserstein metric, on one hand, is an objective function, but on the other hand, it gives me the parameter geometry. And if we look a little bit more closely, when you're passing the derivative to gradient, in functional analysis, we introduce something called rays representation or duality map. So it's really different metric, give you different duality map. And here I give you one example. So the duality map for L2 will be identity, and that's why we always say our L2's dual is L2, which we learn in LP function space theories. But for Wasserstein metric, your duality map is this operator. And as a result, when you have those energy functionals, you plug in, you will get those gradient flow. And those energy are very interesting for kinetic theory. They are very meaningful from statistical physics perspective. We have entropy, entropy plus potential, internal energy, and interaction energy. So suddenly you can derive all the meaningful kinetic equations through Wasserstein gradient flow of meaningful energies. Okay, so optimal transport by definition give us the Wasserstein distance. So the fundamental comparison principle is that I have two probability distributions. They are not the same. So the first goal is how can I make them the same? So for this simple setup, I just transfer some extra mass from the first bin to the second bin. Now they are the same. So once you do this transformation, the second step in optimal transport is to characterize how much effort did we make so that they will be the same. And the way that we quantify the effort is really the key, because the effort is always the amount you move, which is the vertical displacement multiplied by the horizontal change. So every direction, every point is always two directions. One is amplitude mismatch, another is a horizontal transport mismatch. And this is a fundamental difference, in my view, away from, let's say, Sobolev norms or even L1, LP, any LP norms. Because those L2 norms only care about the yellow part, and nobody really care about the horizontal part. So this part is exactly the horizontal part can help us with wave equation inversion and hyperbolic model reduction, etc. And the fourth definition is mimicking the cartoon that I just showed earlier. So f of x denotes the mass you move, so that's the density at that point. And the x minus t of x means the displacement. So these two multiplied together, integrating over the entire domain, is your optimal transport cost among the optimal map. So in my research, I focus on p equal to 2 a lot, but you can also focus on p equal to 1, and you have efficient computation. So next, I'm going to focus on the rest of the talk on why I want to use such a metric and how to use such a metric to solve PDE-based inverse problems that we introduced at the beginning of the talk. Okay, so first of all, I want to emphasize is improving optimization landscape. For anyone who have been dealing with optimization problems, especially non-convex optimization problems, we know most of the difficulty of solving non-convex optimization problems is the fact that gradient descent, Newton's method, BFGS, all those toolbox we get from convex optimization, they become limited because it depends on a very good initial starting point. And it's exactly this good initial starting point that is hard to find, especially is a very large search space like infinite dimensional. Yeah, so that is related to how we use the DG, which is the data metric, to compare the difference between observed data G and the simulated data f of m. So I want to give you a very simple example for the wave problem that I saw we saw at the beginning. So in wave problem, what I want to find is the velocity. But if I guess the velocity wrong, let's say I get it bigger than necessary, then that means when I see the wave, it's going to come to me faster, because when velocity is large, the wave transport faster, so I see it earlier in time. While the red one can be, for example, the correct wave. So when you have perturbation in velocities, what you see in wave in the data aspect are not like a vertical differences. Most of the time you see horizontal differences, and because also wave propagate along the characteristics. And then if I use L2 norm or any LP metric to compare the difference between simulated data and the reference data, then as a function of S, I see a very nasty optimization landscape. And S here is 1 over velocity. I see a very nasty optimization landscape. And I can only guarantee success using all those mature optimization algorithms if I start very close. And this is where the frequency of the wave is limited. And Lauren did a lot of work on broadening up this Bayesian attraction by extrapolating low frequencies from the wave. But the limitation is here in the sense that L2 norm really compares in two vertically and 2 pointwisely, and your data don't have that dependence on the parameter. Alternatively, if you use Wasserstein metric to compare the same two signals up to a normalization, you get a global convex optimization landscape. So from practical perspective, I would like to work with this optimization landscape much more than that, especially their minimizer coincide. So that is one thing. So based on this, we can also prove a lot of properties. I actually did that in many of the papers. The reason I don't want to go into the proof is because I believe fundamentally there is no such a sense of global convexity. The reason is I'm dealing with the space of velocities. And for wave problem, I'm extremely interested in discontinuous, very irregular velocities at, let's say, L2. So in such a large space of search space, I don't think Wasserstein metric is going to be globally convex. But now, if it's not globally convex, what I can hope for is, can I make the Bayesian of attraction, which is the like a strongly convex subregion of the function, can I make that as large as possible? That will be the goal, rather than saying global convexities, because we are really dealing with infinite dimensional optimization problems in inverse problem. Okay. So this is one example that we ran many years ago for a more realistic inversion process. So what I showed you earlier is very toy model, synthetic model that you purely have a translation. But in the real wave situation, you have not only translation, you also have damping, you have superposition, there's noise. The wave look much more nasty. But even in those situations, you can see in this video, starting from the same initial condition, the first column is L2 based inversion. So as the iteration continues, the velocity converts to something that is not physical. While the right, and at the same time, the residual also doesn't go away. Residual is a difference, subtracted difference between the data and the simulated data, the reference data and the simulated data. So we are doing data matching. So if we are doing a good job, eventually the residual should disappear, but it didn't, showing also the sign of getting stuck at the local minimum. On the other hand, the Wasserstein metric reduced the data residual to almost nothing left, and with the correct benchmark recovered. So yeah, coming back to what I think as a more like intuition level, why Wasserstein distance would work in this transport type of problem. So then we really have to go to the optimization, like framework will go to your code to see when is my gradient equal to 0. So when we are doing optimization algorithm practically, when you get stuck, even in machine learning training, for example, when your iteration stops and you see, oh, the performance is not good, that means gradient is 0, but the residual is not. Like you didn't match the data. So this is usually the discrepancy, and we try to get around with that. So now let's examine what can make my gradient equal to 0. So the gradient, which is objective function with respect to parameter, since we are using this data matching thing, so we have two components by chain rule. The first component is the derivative of objective function with respect to the simulated data. The second level is the simulated data with respect to the parameter. So that's chain rule 2 components. Most of the objective function we use, such as L2 norm, KL divergence, Wasserstein metric, or any LP metric, the derivative will never be 0 unless you perfectly match the data. Just use L2 as an example. The derivative is f minus g. The f minus g will never be 0 unless f equal to g. So this thing will never be 0 unless you are already fitting the data. So that is now the worry part. Now let's look at the second term, which is the Jacobian, or the linearization of your forward operator. So in a lot of finite dimensional world, this operator and also faithful parameterization, this operator we reasonably assume is going to be full rank. Because if this operator is not going to be full rank, that means your underlying problem has non-uniqueness. So you wouldn't, the problem is not well posed. So in discretized formulation, we usually assume this is a full rank. So that cannot be the reason you have 0. So with these two components cannot be 0, then there's only one possibility left. It's really the inner product or this combination of the chain rule that give you 0. So another way to think about is the projection of the derivative or data derivative projected onto the column space of your Jacobian, where the linearization of the forward operator is 0. And that is when we see that data is not matched, but gradient is 0. So for the wave problem, we can see this pretty obviously. Because L2 norm want to change the data in vertical direction. That's the nature of f minus g squared. So the derivative, the first component want to go vertical, but the Jacobian want to go horizontal. So there's no feasible velocity that can make wave go vertical. So the projection of these two is 0. And that's why we get stuck. So now for the problem, for the use of optimal transport is precisely to overcome that. Because the feature derivative of optimal transport, with J being the Wasserstein metric, this thing is x minus t of x, with t being the optimal map. So you already know this thing is precisely the displacement. And the displacement is aligned with how wave propagate. And as long as they align, I have a non-zero gradient, and I can keep going in my optimization process. With this understanding, you can also see whether your own problem is a good candidate for using Wasserstein matrix as an objective function. I'm not here to advocate that you should all the time throw optimal transport in your problem, but you can see whether what you need is particular this transport type of alignment. So in another paper with my collaborators, Professor Krieger and Bjornquist, we identify a sequence of other inverse problems in relative vanilla setup in the paper that you can also benefit from it. And some of them are not even related to hyperbolic equations. So what we really need is not the fact that f is a solution of some hyperbolic PDE. What you really need is the dependence or continuous dependence between the parameter and the data is hyperbolic or is transported in nature. That is what's important. So with that being said, you can create hyperbolic phenomena in inverse problem purely using elliptic PDE or parabolic PDE. So for example, I have in elliptic PDE, I have a source term and it's localized. Then once I have the solution is near the source. But if I move the source far away, well, the solution also go far away. So I can create transport phenomenon just because my source changes the location. So this hyperbolic phenomenon is what makes optimal transport successful rather than the PDE itself being hyperbolic PDE. So overall, for example, deconvolution with highly localized source or reconstruction from projections can also be transport dominated. And that's where you can see also benefits of optimal transport. Okay. So with the previous setup, I also want to mention some other contribution in the field. What I was talking about is changing J. So you change the derivative from the data. But there's also very nice contribution in the field in FWI that is focusing on changing this. You can fix dJdF the same, but if you can change your linearization of the forward operator by changing the tangent or the Jacobian structure, you can also make the problem better. So for example, model extension by Sams and Minkoff in many years, and also model reduction by Liliana Boscia very recently. They are both having results demonstrating better optimization performance. But why is that? I think intrinsically is because they are making the Jacobian better while fixing J. Okay, so now we finished property 1, and now I want to mention about property 2, which is the robustness to noise of the Wasserstein metric. So with this demonstration, I want to relate Wasserstein metric as a metric of probability distributions to things like Sobolev norms that we learn in functional analysis. So this connects to several nice works. One is by Felix Otto and Cedric Villani in 2000. They prove in the asymptotic setting, even I compare Wasserstein metric between mu and mu plus d pi, it's asymptotically d pi is h-1 semi-norm. So that tells you it's a little bit weaker than L2, but not so much, only one order. Okay, many years later, it sounds like the non-asymptotic takes a lot more time. Many years later, Remy Priori, not Gabriel Priori, Remy Priori proved that if I have two property distribution, they have densities. In addition, the densities are bounded from above and below by two constants. Then you have a very clean linear equivalence between the Wasserstein metric and the H-1 semi-norm. So that's, again, put W2 in the non-asymptotic setting near the H-1 semi-norm. Okay, so both results are based on the property that you do have absolute continuity with respect to Lebesgue. But if you have singular mu, I think the relationship with H-negative S is even worse, because we know delta function cannot be in H-negative S unless S is bigger than D over 2. So the higher dimension it is, the weaker the Wasserstein metric it is, because Wasserstein metrics always can measure delta, but not all the Sobolev norms can measure delta. So all of those tell us, okay, Wasserstein is one way or another related to H-negative S norm. So what is the H-negative S norm? So there's many definitions through duality, etc. I really like this definition using Fourier transform, because that really tells us what's going on in the way of HS norm is measuring. So let's think we have a very linear problem, AM equal to G. So it's a least square minimization, but rather than least square, I have HS norm instead. But the HS norm is essentially taking a Fourier transform of the input. So that gives us all the hats, hat cassis, hat G delta. And once I have this Fourier transform, I'm going to weigh different frequencies differently. And this is really where the role of S plays. If S is 0, all those red terms is just 1. We just recover our Passover identity or Planchal identity. But when S is positive, that means higher frequency has much bigger weight than lower frequency. So you can think about H2, H3, H higher order norms really concentrate on the higher order derivatives. And inversely, if you have negative S, then you will have much more weight on the lower frequency components of the residual in Fourier domain than the higher frequency components. And most of the time in noise, when I have noise, the noise are oscillatory. So noise represents in the data in terms of higher frequency Fourier component. So if you have a metric that can ignore the higher frequency components, then you can be robust to noise. So the relationship between HS norm and the Wasserstein that connecting when S equal to negative something is precisely damping out the lower frequency components. And if we write it down the solution, since it's linear, so we really have a normal equation, and taking back, we have a very nice weighted least square solution. So the P is the essential preconditioning operator. So when P S equal to 0, then that's identity. But if S is negative, P is the integral operator. And vice versa, when S is positive, is a differential operator. And when the differential operator or integral operator hitting your data noise, you really can cancel out some of the noise delta effect. So this is going to be demonstrated by another example we had early on in wave inversion. So let's say I pollute my data, which is a clean wave field, by this very terrible blue field. And I'm going to use the blue one as the reference to do inversion. So I also have a video. So gradually the Mamouzi model get updated. So you can see the black signal is the black signal is a simulated wave. So it's changing iteration by iteration because it represents the data simulated precisely at this velocity. And it's updated by LBFGS. And after about 80 iterations, the inversion stopped. Like the gradient is 0. So when the inversion stopped, it looks like from the data perspective, there's still a lot of residual. The blue and the black are nowhere near the same. So at the beginning, we were also kind of confused. And then I realized maybe because I'm so used to eyeball norm, like by our eyes, we think the black and the blue are so different. The same with any LP metric. It's so different. But they are almost the same under the eye of Wasserstein metric. And that's why Wasserstein metric can be insensitive to those high frequency mean zero. And to some extent, the higher frequency is better because the higher frequency is the Wasserstein has more damping on it. Okay, so now we move to the final property of the Wasserstein metric. So far I've been using this tool as objective function. So in the sense that I'm using the Wasserstein metrics to compare data 1 and data 2. So one is a reference, another is simulation. I want to minimize them. The third part is to transit a little bit. My objective function is the same, but I'm just going to use Wasserstein geometry to be the one that give me the gradient. So now we are going to use Wasserstein in the M part, which is the parameter geometry. Okay, so first of all, I want to write down gradient descent in a very abnormal way. So when we have this objective function, we can write down the gradient flow, which is a continuous version of gradient descent, like dm dt equal to grad jm. So that's the gradient flow. So once we have the gradient flow as a numerical analysis person, right, you have two ways to do it. I can do forward Euler and or implicit Euler. If I do forward Euler, you recover gradient descent, literally. But if you do implicit Euler, one way to write it down, the implicit Euler, is through this proximal operator. And that's also, I think it doesn't let me to be too close. It is also from the seminal work of JKO paper in 1998. And at the front page, that's what they wrote, implicit Euler in this form. But once you write down implicit Euler as a discretization of the gradient flow in this form, you can see where the dm really play a role. Because different choice of the parameter dm, which is a metric for the m parameter space, can directly change what inversion I'm going to get, or the next iteration I'm going to get. So this is where you see different gradient flow or different way of treating a metric can change your next iteration for one. But if you keep doing that, it really can change your trajectory and eventually where you converge to. And another relative related is the so-called natural gradient. This notion comes from machine learning about late 20th century. So the reason they have natural gradient is in machine learning, as we all know, there's no so-called model. You can use naive Bayes, logistic regression, convolution, generative, fully. There's so many of them. So that's why they were thinking, it's kind of silly if I'm using the parameter metric to decide what's next. Because the parameter can change. The moment I change my model, the parameter will be meaningless. So how about I use the data as the weight I decide the next iteration? The reason is in machine learning, data never change. That's the starting point of everything. So that's where the natural gradient kind of show up. So rather than comparing the difference between M and M sub L, we can lift it up from parameter space to data space. And that lifting give us f of m and f of ml, and then we need to use the data metric d sub g to compare them. And whoever give us the minimum of this is going to give my next iteration. And in many situations, you can prove this is asymptotically Newton, or at least should be Gauss-Newton equivalent. So give you faster convergence, at least. So what we have observed is the fact that choosing different dm or dg, you can change your convergence speed. So it can be faster versus like super linear or linear, or you can actually have a totally different path that we'll show in a moment, and also change your stationary points. So those are the magic I want to emphasize, independent your objective function. So here we fix j. J is the objective function, it's just fixed, it's the same objective function. But just because you choose different metric space to find the m, you can create all the magics of acceleration and also change global convergence. So let's see one example. And this is also I borrow from the language I know the most, the least square reverse time migration. So in this problem is a linear inverse problem solved as a least square regression. And here I choose L2 norm, which is the L2 norm in the problem itself. But I'm using either the L2 as a metric space or H-1 as a metric space. Remember earlier we already see H-1 is weaker than L2, which means the H-1 has more oscillatory things in it. In 1D, H-1 even have delta in it. So it's more oscillatory. When I'm dealing with geological structures, I want things to be oscillatory. I want things to be discontinuous. So I make it even weaker than L2. So when I do the inversion after the same number of iterations, and that's precisely what I see. The L2 inversion is giving this image, and the H-1 giving the other. And the second one is visually more sharp and high resolution than the first one, because you have a faster convergence rate by choosing this metric space. So in another work, we also look at non-convex problem, because when it comes to non-convex problem, different optimization algorithm can totally change where you locate, because we are really in the world of Bayesian attraction. So here, objective function is again fixed. I'm dealing with Gaussian mixture model matching, which is challenging all the time since the multimodal. So I have global minimum, local maximum, and then some saddle points and local minima like outside. So starting from the same place, the L2 natural gradient converge following the flow field diverge to somewhere that is not minimum. But the Wasserstein natural gradient, which means I choose dg to be W2 rather than L2, then I have a totally different trajectory from the same starting point. So the blue signals, blue vector fields is precisely gradient vector fields I visualize. They have the same level set because the J is fixed, so objective function landscape is fixed. But just because you have a different descending mechanism, you can lead your iteration go to a different place. So that means you potentially can achieve global convergence, global optimization, not by changing J, but by warping the geometry. So for example, warping it towards the global minimum. But there's still a lot to understand. I think the difficulty of analyzing it or have a theorem about it has to go through the tools of dynamical system and studying really the basis of attractions. At the final part, just let me emphasize again that gradient is not derivative. I try to emphasize when I teach applied function analysis this semester, and I wish I was emphasized a long time ago. So derivative belong to the dual space of the state. So derivative is really an operator acting on the prime variable. But gradient on the other side is something you add to the parameter. So gradient belong to the prime space. So the relations that go from the dual space, dj delta j delta m, to the gradient is grad mj. That is done through duality map in Ritz representation. So, and we can only cannot be careless about it if you assume automatically, implicit or explicit, that M is L2 geometry. Then there's no difference. But as long as you don't assume L2 geometry, you need to be very careful. And for example, in Wasserstein gradient, we prove it, but I think it's a very standard thing. We just cannot find it elsewhere that people already know in the community. So the L2 gradient, as we just mentioned, since the duality map is identity, is purely delta J delta M. But the Wasserstein gradient is the grad of it. So that tells you the Wasserstein gradient are vector fields. If your original gradient is a function in some dimension, then Wasserstein gradient is going to be vector fields. And you can think about why, because when I change from one distribution to the other, I need to stay positive, I need to stay conservation of mass. But if I just push it using vector fields, I can always conserve those quantities. So it's very natural to use vector fields. And based on that, I also just want to come back very briefly to the Boltzmann equation that I mentioned at the beginning that I learned from Russ Keflich during my time at Courant. So Boltzmann equation is terrible when I first look at it. It's so many symbols and what are those primes? That's really complicated. But there's 12 dimensions because of the integral nature. Without integral is 7, with integral 5, additional 5, so it's 12. So if I have an optimization problem related to Boltzmann equation, have this binary collision, then I want to do this PDE-constrained optimization. That means I have a forward PDE, I have an adjoint PDE. And the adjoint PDE is by nowhere near simple. It's another 12-dimension integral differential equation, right? Then the gradient will be, oh, if you can solve the forward, then you solve the adjoint. Compounding the forward and adjoint solution here, you get the gradient. So that's the standard recipe in PDE-constrained optimization. But if I'm using, just let me go back to here. Those variables, those adjoint variables, we found out using some derivation, they have a meaning. They are not just Lagrangian multipliers. They have a meaning. You can regard them as the derivative of your objective function with respect to intermediate PDE solution. And it's exactly those intermediate PDE solution you don't have access. You can only see them through the simulation of the PDE. And that is, again, the L2 gradient. But if I take a grad of it, that's when I turn L2 gradient to the Wasserstein gradient. And that means those gammas, they are also gradient, but now they are vector fields. And those are the vector fields, precisely what we derive in adjoint of the direct simulation Monte Carlo methods. So direct simulation Monte Carlo method is a super efficient method to simulate that 12-dimensional ugly PDE. But so if I'm using optimization, I'm in an optimization framework, I also want an equivalent, if not more simple, method to solve the adjoint equation. And that can be challenging by looking at the other adjoint equation that we saw at the beginning. But with this understanding that you can change from L2 gradient gammas to Wasserstein gradient bold vector gammas through this simple change, then I also can derive a very efficient adjoint Monte Carlo method. So that now in those papers we prove, or we demonstrate, we can simulate the gradient of Boltzmann equation constraint optimization within a second. And I can do it either on my laptop with 1 million particles. So the efficiency really breaks the hurdle of using those very complex integral differential equations in engineering applications. So finally, I would like to draw my conclusion. The starting point is the inverse problem. And there's a lot of a group of mathematical analysts prove all kinds of beautiful properties about inverse problems, such as existence, uniqueness, stability, for example, Gunter-Woolman. But what I present is, if I want to solve it practically on a computational perspective, I should turn it into optimization. And that is always the universal language. But once you turn it into optimization framework, how you choose the data discrepancy and the model measure geometry, you can also change your performance quite a lot. And almost all my papers are targeting on how you change these two, you can achieve very different result. And I demonstrate some of them, and I think maybe there's more ahead over there. So I'm very happy that I have the chance to share these insights, and I'm looking forward to hear your questions and comments. Thank you very much.
Very interesting talk. Let me check the questions.
We changed the cost function to the difference in constant to norm. Does this make the inverse problem more expensive because you need to solve the linear programming?
Yeah. So basically the question is about the computational cost of solving optimal transport problem. So that's a several level ground, depending on your dimensionality. In my problem is 1D, 2D, 3D. I think they are relatively okay. 1D is analytic, so it's quick sort. 2D or 3D linear programming or solving Monge pair equation or Banach-Linear formulation, they can all do. And if you are in data science application, you usually deal with point cloud. And the curse of dimensionality will show up. It definitely increases with D. So what people do in those applications is to consider what we call sliced Wasserstein distance. So when you do sliced Wasserstein distance, it's like a redown transform. So each time you slice it and it's 1D, another slice is 1D. So always compare the result of the slices. So eventually it's still 1D complexity. And the people also prove that there's some equivalence between sliced Wasserstein metric and the Wasserstein distance that I presented. Yeah, but it's a very good question. Yeah.
I noticed you mentioned all these experiments that you have done in your previous work, right? So do you need to convert the L2 laws to this Wasserstein space for each problem independently, or is there like a general framework, like that can be implemented in a solver?
It's a general framework because if I use the adjoint state method, whenever you change the objective function, you only change one particular term in your adjoint PDE. So different problems, of course, have different adjoint PDE, but the flexibility that you don't need to change the framework, just changing one particular term in the adjoint PDE is where you can be very flexible in incorporating any objective function in your problem. Yeah. Yeah.
So looking at the part of your work concerning the natural gradient and these prox ideas, where you claim that you have, let's go back to the picture with the next one.
Yes, yeah.
So I'm a little curious if you could give us a bit more insight as to what's happening here that might enhance convergence in the context where you have maybe local min. And specifically what I'm looking at is that the G of M didn't change, and the G of M still has those potentially issues and ridges to overcome, things like that. And the only piece of intuition that I have about the prox term that you're adding to it is that you're ensuring that your update is not too long and you have a specific geometry for it, that the update cannot be too long. So what intuition could there be that you could achieve better convergence, specifically, avoid local min?
Yeah, that's a very good question. Let me just find a marker. So when it comes to natural gradient, right? But that's something we can write down. But if you linearize it, waving our hand a lot, then you will have the next iteration, L plus 1, let's say, equal to the current iteration minus the step size. And then that's your normal gradient, which is, let's say, like L2 gradient. Let me say it in that way. L2 gradient of J. So this is the L2. So just to remember that. And then there will be a matrix. So that's why people also claim preconditioning. And this matrix has the following structure: Z transpose L transpose LZ. So what is Z? Z is Jacobian. So it's G. Z is usually what we have df, dm in this particular problem, because I'm minimizing the mean, but what I'm really measuring is the density. So this is the Gaussian mixtures model itself. But the L come from your geometry. So by aligning, so you actually can change the direction by aligning Z and L in one way or another. You can accelerate clearly by, for example, killing all the spectral bias in Z and make it close to identity as possible. But also you can change the direction of it by, it's like a scaling to some extent. Yeah.
So this kind of PSD preconditioning, it won't change the angle of grad J by more than 90 degrees, right?
No, it won't. So that's something I still try to understand, because this tells us locally the direction is warped from this to that. But what this two plot is showing is every step you are changing locally, but eventually you create something that is qualitatively different. That one is local minima and another is global. So I was trying to brainstorm for tools for that, and the only thing that I think could be useful is really from the theory of a dynamical system when we study based on attraction. Because in dynamical system, you can convert to one attractor and another based on where you are standing. So the moment we have this, we are changing the dynamics for sure, and correspondingly, we are changing where the based on attraction are divided. So that's that's the direction maybe.
We're over the hour, so let's thank you, Yunan, again.
Yeah, thank you very much.